Hi guys, welcome back to Quantum Science Hub. In our last video, we have learned chapter 2 with the basics of atoms, elements, compounds, isotopes, and the formation of ions. This is the part 2 video, which is more focusing about chemical bonding. So, if you're ready, let's get started. When atoms of the same type or different types chemically join together, it is known as chemical bonding. Atoms bond together so that they can achieve stable electronic configuration of noble gases. Anyway, do you still remember about stable electronic configuration of noble gases? So let's do a quick review about it. In electronic configuration, the number of electrons allowed to occupy in the first electron cell is 2, while in the second, in the third, in the fourth cell is 8. For example, I have an element named A with 5 atomic number. So the electronic configuration is 2, 3. Next, the atomic number or proton number of B is 10. So the electronic configuration is 2, 8. Next, the atomic number of C is 15. So the electronic configuration is 2, 8, 5. And finally, the atomic number of D is, let's say it's 19. So the electronic configuration is 2, 8, 8, 1, right? So this is what we call valence electron. If you still remember, what is valence electron again? Valence electron is the electron in the outermost cell, right? So for element A, C, and D, it is not full or it is not 8. So that is what we call it is not stable, right? Not stable. While element B is stable because the valence electron is 8. So that is what we call the stable electronic configuration of a noble gas. Okay? There are 3 types of chemical bonding that we will learn in this chapter, which is ionic bonding, covalent bonding, and metallic bonding. Now let's talk about ionic bonding. So ionic bonding is a transfer of electrons from one atom to another atom. Okay, let's see in this example, I have lithium. As we know, the atomic number of lithium is 3, right? So the electronic configuration is 2 in the first cell and 1 at the second cell, right? So the metal will lose electron, okay? It will bond with another non-metal, in this case is fluorine. So fluorine, the valence electron is 7, right? So it is a transfer of electrons from lithium to fluorine. And this is what we call the ionic bonding. So this is the formation of ionic bonding. Since lithium loses 1 electron, so that's why it has 1 positive in here. The charge will be positive. Remember, electron is something negative. If you lose something negative, you will become more positive, right? And the electron here is transferred to fluorine. So don't forget, after its transfer, you have the dot in here. And you have to put the bracket. And how many electrons that fluorine get from lithium? It's 1 electron. So that's why the symbol here is negative. If it receives 2 electrons or 3 electrons, it's going to be 2 negative or 3 negative. Okay? So an ionic bonding occurs between metal and non-metals. Metals lose electrons to form positive ions, while non-metals gain electrons to form negative ions. So the chemical bonds between the positive ions and negative ions is called ionic bonds. The ionic bond is a very strong electrostatic force between positive ions and negative ions. The compound containing ionic bond is called ionic compound. Ionic compounds have giant ionic lattice structure composed of oppositely charged ions throughout the crystal. Now, what is the meaning of giant ionic lattice structure? Imagine a huge organized crowd where positive ions and negative ions are holding hands with each other in a varied direction, up, down, left, and right. So this organized arrangement repeats itself over and over throughout the whole crystal, like a never-ending 3D pattern. And that's what we call a giant ionic lattice. Because there are so many ions all attracting each other at once, the whole structure is held together very strongly, which is why ionic compounds are very hard and have high melting points. Now let's take a look at the example here. Sodium chloride and ACl is made up of sodium ions, or positively charged. As we know, sodium is a metal, right? All metals will have positive ions. And chloride ions. Chloride is a non-metal. So all non-metals will have negative ions. Okay? Chloride ions, negatively charged, arranged in a regular pattern known as lattice. The ions are held strongly by electrostatic forces in the lattices. So the structure is going to be like this. As you can see, an A positive or sodium ions are held together with chloride ions. And the bonding between them, this is what we call ionic bonding because they are held with a strong electrostatic forces between the positive and negative ion. So this is how the giant ionic lattice structure of sodium chloride. Now let's see the example how the formation of ionic compound. Draw a dot and cross diagram to show the bonding in magnesium fluoride MgF2. So first of all, we have to draw the dot and cross diagram of magnesium and fluoride. So what is the atomic number of magnesium? 12, right? So 12 Mg. So how we configure this one? 2, 8, 2. So the valence electron here is 2, while the atomic number of fluorine is 9. So 2, 7. So the valence electron here is 7. So in this case, Mg is 2, right? It's better for you to lose 2 more electrons. So that's why Mg becomes 2 positive. And fluorine is better to receive 1 more electron. So in this case, fluorine will become 8 rather than lose 7 electron. So because fluorine receives 1 electron, and that is why the valency here is negative 1, and magnesium loses 2 electrons, so that's why the valency here is 2. And the number of atoms get involved, how many magnesium that we have? 1 magnesium. How many fluorine that we have? F2. So that means there are 2 fluorine atoms. And the total number of getting involved is just times this and this. 2 times 1 and then 1 times 2. The total number of electrons getting involved is 2 electrons. So this is how the formation of MgF2. We have 1 magnesium and 2 fluorine, right? So magnesium in this case will lose 2 electrons. That is why the charge here is 2 positive. And each fluorine atom will receive 1 electron from magnesium. So the electron will transfer to both fluorine in this case. So 1 fluorine will receive 1 electron. So that is why fluorine will become stable in this case. How many valence electron fluorine has at the end? 7 from itself and 1 from magnesium. So the valence electron now is 8, which is stable or complete, right? While magnesium loses 2 electrons, so that's why magnesium also becomes stable, which is 8. And the same thing with fluorine in here, the same, which is 8. Now, every atom in this compound already stable. Why? Because they already reached the stable configuration of noble gases. So this is how the formation of MgF2. Now let's see another example here. Draw a dot and cross diagram to show the bonding in aluminum oxide Al2O3. So first of all, we have to draw the dot and cross diagram of aluminum and oxygen. That is how it looks like. Okay, as we know, the atomic number of aluminum is 13, right? 13 aluminum, while oxygen is 8. Okay, so how we configure aluminum and oxygen? So the electronic configuration will be 2, 8, 3. So the valence electron for aluminum is 3 and oxygen is 6. The valency here, it means how many number of electron that is removed or lose from aluminum is 3, right? So that is why aluminum is Al3 positive, While oxygen here, it's better to gain 2 more electrons to become stable. At the end, the valence electron will become 8, which is stable. Okay, because it gained 2 more electrons, and that is why the ions of oxygen is O2 minus. Now, the number of atoms getting involved based from the chemical formula, Al2, that means there are 2 aluminum, okay? And oxygen, we have 3 oxygen. So the total number of electrons getting involved in aluminum is 3 times 2, which is 6. And in oxygen is 2 times 3, also 6 electrons, right? And this is how the formation of Al2O3. As you can see, aluminum, it loses its third cell. Now it only contains of 2 cells, right? And the second cell is full or stable. And the charge here will become 3 positive. The same thing happens with oxygen. Okay, don't forget to put the charge in here. It's 2 minus, right? And how many aluminum that is getting involved? There are 2 aluminum. So the number here indicates the aluminum atoms involved in this bonding. If you want to have the clear structure, how is the transfer for 2 aluminiums with 3 oxygens? So that is how it looks like. Aluminum has 3 valence electrons, right? While oxygen has 6 valence electrons. So 2 electron is transferred to the first oxygen. So it's in here. Now the oxygen here will have 8 electrons, which is already stable. And 2 more electrons is transferred. Now the second oxygen is also stable because the valence electron now is 8. And the same thing with this. Now everybody is complete or stable. Oxygen will have 8 valence electrons, while aluminum loses their third cell. Now it contains only 2 cells and it is complete, which is also 8 electrons at the second cell. And there is another way to represent an ionic compound. For example, like this. So in this case, you just need to put the dot and cross diagram to show the outer shell only. So you just put the valence electron position here. And after that, after they make an ionic bonding, so in this case, the metal, which is magnesium, will lose 2 electrons and will become Mg2 positive, while these 2 electrons will shift or move to oxygen, right? So this is the diagram or the structure. And here is the physical properties of ionic compound. So note that all ionic compounds or ionic bonding will have high melting point and high boiling point. And the reason is the electrostatic force between the positive and negative ions is very strong. So more energy is needed to overcome it. And all ionic compounds can conduct electricity only in molten or in aqueous solution. So that means it can only conduct electricity in a liquid state. And this is because the giant lattice structure, or we can say the solid structure, has broken down. Electricity is conducted when ions move around freely. Another property is in solid state, it cannot conduct electricity. Why? In solid state, the ions cannot move around freely because they are held strongly by the electrostatic force in the giant lattice structure. And remember, all ionic compounds, they are non-volatile. Non-volatile means they are not easily to evaporate. Why? Because their ions are held together by very strong electrostatic force that require a lot of energy to separate or to break it down. Ionic compounds are generally soluble in water, but insoluble in organic solvents, for example in alcohol. In ionic compound, the bigger the charges on the ions, then the stronger the electrostatic force. The melting point and boiling point are higher also. For example, the melting point of magnesium oxide, which is Mg2 positive and O2 negative, is higher than sodium chloride and A positive and Cl negative. So imagine the charge of an ion is just like the power. So an A positive, right? So you have 1 electron in here at the valence shell, and chlorine you have 7. So it's just like one time of transfer. While in magnesium and oxygen, you have magnesium have 2 valence electron, right? While oxygen have 6 valence electron. So it's just like the double transfer of power. And this is the reason why the melting point and boiling point of magnesium oxide is higher than sodium chloride. Okay, now let's see the word example 1. Magnesium oxide MgO and sodium chloride and ACl are both ionic compounds. The melting point of magnesium oxide and sodium chloride are 2800 Celsius and 801 Celsius respectively. Explain why the melting point of magnesium oxide is higher than that of sodium chloride. And note that you have to see the mark in here, and it is 2 marks. So how to answer this question? So the solution to answer this question is you have to say the charges of Mg2 positive and O2 negative are higher than that of an A positive and Cl negative. By saying this only, you got 1 mark. And then since this question is a 2 marks question, then you have to say something else. So there are more energy is needed to break the stronger. MgO is stronger, right? Than an ACl. So there are more energy that is needed to break it. And by saying this, you get 2 marks. And this is an example of IGCSE past paper question for chemistry. Most of the students, they know how to answer this, but they only got 1 mark. Why? Because they only say the charges of Mg2 positive and O2 negative are higher than that of an A positive and Cl negative. That's all. Without saying more energy is needed to break the stronger ionic bonds, you cannot get 4 marks. So please pay attention how to solve and answer the question. You have to pay attention about how many marks that is needed for this question. Okay? Now let's see another example. Draw and write down the formula of the compound, a dot and cross diagram to show the bonding for the following ionic compounds: between aluminum and chlorine, between lithium and oxygen, between calcium and nitrogen. Okay, how to solve this question? So between aluminum and chlorine, so we have to draw the structure like this. As we know, the atomic number of aluminum is 13, right? So 13 aluminum. Okay, so the configuration is 283. This is the valence electron, 3. While chlorine is 17, so 17 chlorine, 287. So the valence electron for chlorine is 7. So in this case, we need 3 chlorine, right? Each valence electron in aluminum will transfer to 3 chlorine. Okay, then let's draw it. Aluminum will have 3 valence electron, while chlorine have 7, right? So each electron from aluminum will be transferred to chlorine in this case, right? Like this. So now chlorine will have complete or full valence electron, okay, which is 8. So every chlorine will have 8 valence electron, while aluminum will lose its third shell. It only contains of 2 shells, which is also 8 or full, right? Okay, so you can draw like this. So you don't have to draw 3 chlorine. You can just put the number, how many chlorine it is needed. So for 1 chlorine, there are 7 valence electron and 1 dot in here because it is transferred from another atom. And don't forget to put the valency in here, which is 3 positive for aluminum and negative for chlorine. So the formula for this compound is AlCl3. Now let's see between lithium and oxygen. As we know, the atomic number of lithium is 3. So 3 Li. What is the electronic configuration? It's going to be 2, 1. Okay, and this is the valence electron. While oxygen is 8. So the electronic configuration is 2, 6. So lithium will lose 1 electron and oxygen will receive 2 more electrons from lithium. right? So we need how many lithium in this case? We need 2 lithium, right? So the structure is going to be like this. So lithium will lose 1 electron, and that's why the charge here is positive. Okay, and oxygen will receive 2 electrons from 2 lithium. Okay, 1 lithium will transfer 1 electron in this side, and the other lithium will transfer 1 electron to this side. Since oxygen gained 2 electrons, and that's why the charge here is 2 minus. Okay, and that's why the formula of this compound is Li2O, because you need 2 lithium and 1 oxygen. Next, between calcium and nitrogen. As we know, the atomic number for calcium is 20. So 20 calcium, the electronic configuration is 2A8, right? This is the valence electron. And nitrogen is 7. So 2, 5. And this is the valence electron. How we configure this one? Since calcium will lose 2 electrons, so that's why calcium, the charge is going to be 2 positive. And nitrogen will gain 3 more electrons, and nitrogen will become 2A, right? So Ca2 positive with and 3 minus, because you gain 3 electrons. So what is the chemical formula? So it's going to be Ca3 and 2. So we need 3 calcium and 2 nitrogen. So this is how it looks like. So Ca, the charge here is 2 positive, and we need 3 calcium, right? While nitrogen will receive 3 electrons from calcium, okay? And the charge here is 3 minus, and we need 2 nitrogen, okay? And the chemical formula here is Ca3N2. Now let's talk about covalent bonding. Covalent bonding is a sharing of electrons equally between atoms of nonmetals in order to attain the electronic configuration of noble gas. The number of covalent bonds between the elements depend on the number of pairs of shared electrons. In single bond, there are 1 pair of shared electrons. So for example, I have 1 atom and another atom, and they are sharing 1 pair of atoms. So this is what we call 1 pair of electron, okay? And this is single covalent bond between X and X. Next, for example, I have Y, and they are sharing 2 pairs of electron like this. And this is what we call double covalent bond between Y and Y. And it's the same with 3 pairs of shared electrons. So that means it is triple covalent bond. Now let's see how to draw a dot and cross diagram in covalent bonding. A dot and cross is a way to demonstrate the sharing of electrons between nonmetals. For example, as we all know, hydrogen have only 1 proton, right? So how we configure hydrogen? Just 1. To become stable, the first electron cell should be 2, right? So the only way to become 2 is you have to gain 1 electron. So the valence electron in here, which is only contained of 1 shell, will become 2, and it is complete or stable. This is what we call covalent bonding because they are sharing of electrons, okay? Now, at the end, hydrogen will share 1 pair of electrons, and this can be represented as H, and there is 1 line in here. It means hydrogen is a single covalent bond. So a single line here represents a pair of shared electrons. Now let's see the word example here. Draw a dot and cross diagram to show the bonding of fluorine gas or F2. Here is the valence electron for fluorine. As we know, the atomic number for fluorine is 9. So the electronic configuration is 2, 7. So the valence electron is 7. What we need to draw is the valence shell only, okay? So how many valence electrons each fluorine have at the end? So 1, 2, 3, 4, 5, 6, 7 electrons from itself and 8 electrons from another fluorine, right? So in this case, they are sharing 1 pair of electrons. And now, this fluorine will become 8. The valence electron is full or complete, which is stable. The same thing with these fluorine as well. So they have one pair of sharing electron, and this is what we say a single covalent bond. Next word example. Draw a dot and cross diagram to show the bonding in water, H2O. So we need 2 hydrogen and 1 oxygen. Hydrogen only contains of 1 electron. The atomic number of hydrogen is 1. So that's why it only contains of 1 shell, which is also 1 electron, while oxygen is 8. So the electronic configuration here for hydrogen is 1 and oxygen is 2, 6. So the valence electron is 6. So the formation of H2O in here is like this. We need 2 hydrogen at left and right and oxygen in the middle, and they are sharing 1 pair of electron. So in this case, hydrogen will become stable because the valence electron is 2, while oxygen will also become stable as well because it contains of 6 electrons from itself and 7 and 8 at the end. So everybody in here is complete or stable. And this is the single covalent bond between HOH. Okay? Next example. Draw a dot and cross diagram to show the bonding in carbon dioxide, CO2. In here, we have to know the electronic configuration for carbon and oxygen. So as we know, the proton number for oxygen is 8. So the electronic configuration is 2, 6. And the atomic number for carbon is 6. So the electronic configuration is 2, 4. What we need to draw is the valence electron only. Okay, so the valence electron is 6. So that's why you draw in here there are 6 electrons and there are 4 electrons for carbon. So the formation of CO2 in here is like this. Now they are sharing 2 pairs of electrons between oxygen and carbon. So in this case, oxygen in here will have 6 electrons from itself and 2 more from carbon, which is sharing together. So 6 plus 2 is 8, and oxygen now is complete or full, right, which is 8. While carbon in here is also 8. 4 from itself plus 5, 6, 7, 8. Okay, so carbon in here is also complete, okay? In here, this is what we call double covalent bond because there are 2 pairs of sharing electrons between oxygen and carbon. Next example. Draw a dot and cross diagram to show the bonding in nitrogen gas, N2. So in this case, we have to know the atomic number for nitrogen, which is 7. So the electronic configuration is 2, 5. So nitrogen has 5 electrons at the outermost cell. Okay, so in here is 5 electrons. The same thing with this dot and cross diagram, right? So the formation of N2 is triple bond. Okay, so 5 from itself, 6, 7, 8. So there are 3 pairs of sharing electrons together. So in this case, the nitrogen at the left side is 5 plus 3, which is 8. And the same thing with the nitrogen at the right side. 5 plus 3 is 8. So both nitrogen in here is full or stable because they already reached the full or complete electronic configuration at the second cell. And because they are sharing 3 pairs of electrons together, so we have 3 dash in here between nitrogen and nitrogen. And this is what we call triple covalent bond. Now let's see the next word example. Draw a dot and cross diagram to show the bonding in methane CH4. So this is the structure. And as we know, the atomic number of hydrogen is 1. So that's why the electronic configuration here is only 1. While carbon is 6, right? So the electronic configuration is 2, 4. What we need to draw is the valence electron only, which is 4. And in this case, we need 1 carbon and 4 hydrogen. So the formation of CH4 is going to be like this. 1 carbon and 4 hydrogen, right? They are sharing 1 pair of electrons. Okay, so in this case, hydrogen now have 2 valence electrons in the first cell. Okay, so every single hydrogen in here will have 2 valence electrons in the first cell. And carbon will have 4 from itself, 5, 6, 7, and 8. So that's why carbon will also become complete or have full valence electron at the second cell. So all the elements in CH4, they already stable. And it is a single bond. So in here, we draw one line, okay? So it represents a single bond between carbon and hydrogen atoms, okay? Now let's talk about the physical properties of simple covalent compounds. The simple covalent molecules are attracted by weak intermolecular force. The intermolecular force is overcome easily by heating, so the simple covalent molecules has a relatively low melting point and low boiling point. I already summarized the physical properties of simple covalent compounds in this table. The first physical properties is simple covalent compounds will have low melting point and boiling point. Why they have low melting point and boiling point? This is because the attractive force between the molecules is very weak. So less energy is required to overcome it. And they cannot conduct electricity in any state. Okay, what is the state in here? It means they cannot conduct electricity in solid, liquid, or gas. Why? Because they do not have ions which can move about to conduct electricity. And finally, they are volatile. Volatile means evaporates easily because their molecules are held together by weak intermolecular forces that require little energy to separate. And please remember again, the simple covalent compounds generally, or we can say most likely, are soluble in organic solvents like alcohols, but not in water. That means they cannot dissolve in water. Okay? Now let's talk about giant molecular structure. A giant molecular substance is formed by a large number of atoms covalently bonded by one another. The structure is a network of strong covalent bonds. Okay, as we know, generally, covalent bonds is weak, right? Because they are bonds with weak intermolecular forces. But in this case, if they are giant molecular structure, they will have strong, it's not weak, okay? It's strong covalent bonds. And therefore, a giant covalent molecule has significantly different physical properties than a simple covalent molecules. Carbon is a non-metal element which is able to produce a giant molecular substance such as diamond and graphite. So diamond and graphite are the allotropes of the carbon element. So what is allotropes? Allotropes are different structures formed by the same element. So diamond and graphite is the allotropes of carbon. So that means diamond and graphite is just made up of carbon, but their structure is totally different. Now let's see the structure of diamond. It has a giant three-dimensional structure in which each carbon atom is covalently bonded to 4 other carbon in a rigid tetrahedral structure. This is the structure. And this is the carbon atom in here. This is the covalent bond between carbon and carbon. So diamond is hard because of the strong covalent bonds between carbon atoms in a rigid three-dimensional tetrahedral structure. Diamond does not conduct electricity because of the absence of free electrons since each carbon is covalently bonded to 4 other carbon atoms. Diamond is used in cutting and drilling equipment because it is hard since it has strong covalent bonds between carbon atoms in the rigid three-dimensional tetrahedral structure. Now let's see the structure of graphite. It has a giant three-dimensional structure in which each carbon atom is covalently bonded to 3 other carbon atoms in a layer of 6-sided rings with weak attraction forces between the layers. And here is the structure of graphite. So there are 1, 2, 3, 4, 5, 6-sided rings with weak attraction forces between the layers. So this is the first layer, or I can say the top layer, and this is the second layer or the bottom layer. As you can see in here, this is the carbon atom, and this line shows the covalent bonds between carbon and carbon, and this is the weak forces between the layer. Okay? Graphite is soft because of the weak attraction forces between the layers that allows them to slide past each other. Graphite conducts electricity because it has free electrons that can move between each layer. So the uses of graphite here as the lubricant because it is soft, and as electrode because it can conduct electricity in electrolysis process. Now let's see the structure of silicon dioxide, SiO2. Silicon dioxide, also known as silicon 4 oxide, it is a giant three-dimensional tetrahedral structure in which each silicon is covalently bonded to 4 oxygen atoms, and each oxygen is covalently bonded to 2 silicon atoms. Here is the structure. This is gonna be silicon and this is gonna be oxygen, right? So one silicon atom bonded to 4 oxygen atoms, and one oxygen atom is bonded to 2 silicon atoms. Okay, this line here represents the covalent bonds between the atoms. And here is the structure, so it's gonna be easier for you to understand. So from here, we know a tetrahedron is formed which is similar to the structure of diamond. So I can say the structure of silicon dioxide is exactly the same with diamond. The difference here is diamond only contains of carbon element. So one carbon bonded to 4 other carbon atoms. Okay? Now let's talk about metallic bonding. The atoms of metallic elements have the tendency to lose electrons. When the atoms lose electrons, they become positive ions. Please remember again, electron is something negative. If you lose something negative, then you will become more positive, right? In metals, the metal lattice consists of positive ions surrounded by a sea of electrons. The sea of electrons are electrons from the metal atoms which are delocalized. They are free to move about between the positive ions. So metals are good conductor of electricity. Okay, so this is one of the most common questions in IGCSE for this chapter. Why all metals are a good conductor of electricity? The answer is because the presence of free moving electrons between the positive ions, right? Okay, please remember that. The metallic bonding is a strong electrostatic force between the sea of electrons and positive metal ions. And this is the structure for metallic bonding. And the positive here, this is what we call the positive charge of metal ions. And this is the delocalized electrons. Metals are malleable. It means they can be hammered into shape. This is because the atoms are arranged in layers which can slide over each other when force is applied. Most metals are ductile. This means that they can be pulled into wires. This is also because the atoms are arranged in layers which can slide over each other when force is applied. Look at this diagram. Metal atoms are arranged in neat, tidy layers, like a stack of marbles. And between those layers, they can actually slide past each other. When you apply a force to a metal, those layers of positive ions glide smoothly over one another. The whole structure shifts, but it stays together. The metallic bonds which contain of delocalized electrons act like a kind of invisible glue that holds everything together even as the layers move. That's why metals are malleable. You can hammer them flat, especially when the metal is hot. And ductile. It means that you can stretch them into wires. The layers slide, but the metal doesn't snap. Compare that to something like salt or glass. Those have rigid lock structure. If you force them too hard, then they will crack and shatter instead of bending. So next time when you see a blacksmith hammering hot iron or a factory pressing aluminum into a car door, that's millions of atomic layers sliding past each other all at once. So that's all about this chapter: atoms, elements, and compounds. We will discuss some past paper questions related to this topic in the next video. Thanks for watching. Don't forget to like, comment, and subscribe. See you in the next video. Bye!